In Chapter 5, we're going to begin looking at identities. An identity is an equation that is true for all values in the domain. The reciprocal identities were discussed in Chapter 4. Let's agree that the cosecant of an angle is equivalent to 1 over the sine of that angle. This is true for all 6 trig functions. So we could also write that the sine of theta is equal to 1 over the cosecant of theta. These are called our reciprocal identities. The next set of identities is the quotient identities. These were also discussed in Chapter 4, but let's review. The tangent of an angle, theta, is equivalent to the sine of theta divided by the cosine of theta. This is true for any angle theta. Therefore, it is also true then that the cotangent of theta is equal to the cosine of theta divided by the sine of theta. In a few problems later on, you can substitute cotangent for cosine over sine, or tangent for sine over cosine, to help you simplify an identity. We now need to discuss the Pythagorean identities. There are 3, one main identity, and 2 that are offshoots from the original. The original Pythagorean identity is sine squared theta plus cosine squared theta equals 1. This is an identity, which means that for any angle theta, this must be true. Now, let me show you where this comes from. If we take a point on the unit circle, and let's just take a point in quadrant 1 to make life simple, and let's use a 30-degree angle. This point out here has coordinates √3 over 2 and 1/2. If you recall from Chapter 4, the x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the angle. So if this is 30 degrees, we know that x is equal to the cosine of 30 degrees, which is √3 over 2. And y is equal to the sine of 30 degrees, which is 1/2. If we take those values and put them into the original Pythagorean identity, you will see that the answer comes out 1. So, sine squared of theta, sine of theta is 1/2. So we take 1/2 and we square it. We add it to the cosine of theta squared, which is √3 over 2 squared, and we need to show that that is equal to 1. 1/2 squared is 1/4. √3 over 2 squared will give you 3 over. The second 2 Pythagorean identities come from the first one. We're going to take the original Pythagorean identity and we're going to divide every term by sine squared theta. So we start with sine squared theta plus cosine squared theta equals 1. Dividing every term by sine squared theta, we will produce the second Pythagorean identity. Sine squared over sine squared makes 1. Cosine squared over sine squared makes cotangent squared theta. And 1 over sine squared makes cosecant squared theta. I suggest that you not memorize this second one, but know how to produce it from the original. It's much faster than trying to memorize. The third Pythagorean identity comes very similar to the second one. Instead of dividing each term by sine squared theta, you need to divide each term of the original Pythagorean identity by cosine squared theta. So if we take sine squared theta plus cosine squared theta equals 1, dividing every term by cosine squared theta, you will see that we can produce the third Pythagorean identity. So sine squared over cosine squared makes tangent squared theta. Cosine squared over cosine squared makes 1, and 1 over cosine squared makes secant squared theta. Again, I highly suggest you not memorize this one, but that you know how to get it. Know that secants and tangents work together, just as in number 2, cotangents and cosecants work together. Now let's look at problem 1 off of the worksheet. You are asked to find the sine of theta and the secant of theta if the cotangent of theta is negative 1/3 and cosine is positive. We would have used a reference triangle in chapter 4. This chapter we're going to use Pythagorean identities. Since I know the cotangent, I will be using identity number 2. 1 plus cotangent squared theta is equal to cosecant squared theta. Replacing the cotangent squared with negative 1/3, you get 1 plus negative 1/3 squared equals cosecant squared theta, which produces 1 plus 1/9 equals cosecant squared theta. 9/9 plus 1/9 makes 10/9 equals cosecant squared theta. Square root both sides, and you now have that the cosecant of theta is equal to the root of 10 over 3. Now you need to determine if this value is positive or negative. So we have to look at our all students take calculus. Since we know cotangent is negative, but we know cosine is positive, we must be in quadrant 4. Therefore, cosecant in quadrant 4 is negative. We now have the cosecant of theta. We need the sine of theta, so take the reciprocal. Sine of theta is going to equal negative 3 over root 10. And when you rationalize, you then have the sine of theta equals negative 3 root 10 over 10. That's the first answer. Since we now have the sine of theta, we can use that in the original Pythagorean identity to find the cosine of theta, and then take the reciprocal to find the secant of theta. I'm going to use the sine of theta in the expression where it is unrationalized. It will be simpler to use. So the sine of theta is equal to negative 3 over root 10. Substituting into the original Pythagorean identity, you're going to get negative 3 over root 10 quantity squared plus cosine squared theta equals 1. Squaring the first term, you get 9 over 10 plus cosine squared theta equals 1. Subtracting the 9/10 from both sides, you have cosine squared theta equals 1/10, and then square root. Cosine of theta equals 1 over root 10. Again, we are in quadrant 4, so the cosine value will be positive. You needed the secant of theta, so take the reciprocal, and the second answer to problem 1 is that the secant of theta is equal to the root of 10. You have now found the sine of theta and the secant of theta using Pythagorean identities. On problem 2, we need to simplify the expression negative tangent of x times cosine of x. When you simplify a trig expression, you usually need to use some type of identity to produce one trig function only. I'm going to write the tangent of x in terms of its quotient identity. So I have negative sine x over cosine x times cosine x over 1, making them both fractions. Now, as you can see, you can cross-cancel the cosine of x, leaving you with negative sine x. You now have taken an expression that contained two trig functions and rewrote it as an expression containing only one trig function. That is how you will simplify an expression. If we look at problem number 3, we again have two different trig functions. We have the secant of alpha over the cosecant of alpha. Oftentimes it is very helpful to rewrite the expression in terms of sine and cosine. So secant of alpha is 1 over the cosine of alpha, which is being divided by cosecant, which is 1 over the sine of alpha. If we then divide two fractions, we copy dot flip. So we get 1 over cosine of alpha times, and flip the second fraction, sine of alpha over 1. Multiplying together, we then get the sine of alpha over the cosine of alpha, which is the quotient ratio for tangent. Therefore, this simplifies to the tangent of alpha. On problem number 4, we need to use our factoring skills. We begin with the sine cubed of x plus the sine of x times the cosine squared of x. If you think back to algebra, if you notice both expressions, both terms of the expression have a sine x. Let's take that sine x out. That would be the GCF. If I factor out the sine of x, I am left with the sine squared of x plus the cosine squared of x. You need to become very familiar that sine squared plus cosine squared is a Pythagorean identity that is equal to 1. This expression is equivalent to 1. So what I really have is the sine of x times 1. So this expression simplifies down to the sine of x. You need to look for Pythagorean identities when you're trying to simplify expressions in trigonometry. On problem number 5, the first step is to multiply the numerator together. We have cosecant of x minus 1 times cosecant of x plus 1 all over cosine squared x. The numerator is a difference of two squares, so if you FOIL this out, the first terms will give you cosecant squared x. The outer and inner terms will cancel, and you get minus 1 for the last terms. This is now divided by the cosine squared of x. Now, you need to think back to your Pythagorean identities that we did at the beginning of the lesson. There was a Pythagorean identity that said 1 plus cotangent squared x equals cosecant squared x. If we subtract the 1 over, we then now have that the cotangent squared x is equal to the cosecant squared x minus 1. That substitution can now be made into our expression. So the numerator, cosecant squared x minus 1, becomes cotangent squared x. That is still divided by the cosine squared of x. If I now take the numerator and rewrite it in terms of sine and cosine, this becomes cosine squared x over sine squared x divided by cosine squared x. Take the denominator, put it over 1, and now you can see division of two fractions. So we get cosine squared x over sine squared x times 1 over cosine squared x. Cross canceling, you then get 1 over the sine squared of x, and 1 over sine squared, using reciprocal identities, is cosecant squared x. And now we have simplified the expression down to one trig function. On problem number 6, we have to subtract two fractions. In order to subtract or add fractions, you must have a common denominator. So we will need to take the denominator of the second fraction and multiply it top and bottom to the first fraction, and the denominator of the first fraction and multiply it to the top and bottom of the second fraction to create the common denominator. So we have the cosine of x over 1 minus the sine of x. This must multiply by the cosine of x over the cosine of x. In the second fraction, we have to take the sine of x over the cosine of x, and we have to multiply top and bottom by 1 minus sine x over 1 minus sine x. We now can get a common denominator of cosine x times 1 minus sine x. Our numerator in the first fraction will be cosine times cosine, which is cosine squared x. You must then distribute the negative sine x into the parentheses, which gives you negative sine x plus sine squared x. Now, using Pythagorean identities, cosine squared plus sine squared is equal to 1. So our numerator becomes 1 minus sine of x over cosine of x times 1 minus sine of x. Since we have a common binomial top to bottom of 1 minus sine x, we can cancel this 1 minus sine x with this one, leaving us with 1 over cosine of x. And 1 over cosine of x is equal to the secant of x. So by finding the common denominator and using Pythagorean identity, I can simplify the original two fractions down to the secant of x. The next two problems require that you use your algebra factoring skills on trig expressions. Let's look at problem number 7. We are given that the secant squared of x minus 2 secant of x plus 1 can be factored. Now, if you want to think of it in terms of algebra, secant squared x could be thought of as y squared minus the secant of x would then be y. So this is 2y plus 1. These two equations are exactly the same. The first one is written in terms of a trig function. The second one is written in terms of y. If we are going to factor this, we need two numbers that multiply to 1 that add to negative 2. So we would get y and y minus 1 and minus 1. This then is the same expression above using the trig equation. So in the trig form, it would look like the secant of x minus 1 times the secant of x minus 1. If you would like to condense this, you could write it as the secant of x minus 1 quantity squared. You have to learn to see the trig equations as algebraic equations. On problem number 8, you have a problem with the fact that you have a cosine x along with a sine squared x. It is difficult to factor a trig expression that has two different trig functions. So we need to make a substitution. Now, the Pythagorean identities only work for squared terms. So let's go back to the original Pythagorean identity. We have that the sine squared of theta plus the cosine squared of theta is equal to 1. If I subtract the cosine squared to the other side, I can find out that the sine squared of theta is equal to 1 minus cosine squared of theta. Now, I can replace the sine squared x in this problem with 1 minus cosine squared x. That will give me an equation all in cosines. So we have the cosine of x minus 2 parentheses. Substituting, I have 1 minus the cosine squared of x minus 1. Let's distribute the negative 2 through. We have the cosine of x minus 2 plus 2 cosine squared x minus 1. If we write this in descending order and combine like terms, we end up with 2 cosine squared x plus cosine x minus 3. We now have to factor this trig expression. Using my factoring skills, 2 cosine squared x has to be a 2 cosine x and a cosine x. Since the middle term has to have a 1, I will need to put the 3 here and the 1 here. The outer terms now make 2 cosine x. The inner terms make 3 cosine x. Since the middle term is positive, you need a plus on the 3 and a minus on the 1. If you FOIL this out, you should get back to the equation above. The last part of the worksheet deals with co-function identities, even and odd identities. I will discuss co-function identities when I return to class. Let's talk for a moment about odd and even identities. This material should make sense back to semester 1. Recall that if a function is odd, when you replace negative x, you get the opposite of the function. Sine is an odd function. Therefore, if I take the sine of a negative angle, that should equal the negative of the sine of the positive angle. This also works for tangent, who is an odd function, and both of their reciprocal functions, which are cosecant and cotangent. Let me show you that this is true. Let's look at the sine of negative pi over 6. Does that equal the negative sine of the positive angle pi over 6? Using our reference triangle, this is 30, this is 60. We have 1, root 3, and 2. The sine of a 30-degree angle is 1/2. If we are at negative pi over 6, we are in quadrant 4. Therefore, the left hand of this equation would give me negative 1/2 because sine is negative in quadrant 4. If we look at the right-hand side of the equation, sine in quadrant 1, pi over 6, is 1/2, and the negative sign out front makes that negative 1/2. As you can see from the example, the sine of negative x will always equal the negative sine of x. This is also true for the tangent function, who is also an odd function. Therefore, the tangent of negative x will always equal the negative tangent of x. If we look at the cosine function, recall that the cosine function is even. An even function says that if you replace x with negative x, you get back the original function, which is just cosine of positive x. Let's also show that this works. Again, let's look at our pi over 6 angle. So if we have the cosine of negative pi over 6, is that equal to the cosine of pi over 6? Using the reference triangle, we need to find the cosine of a 30-degree angle. So here's 30, here's 60. We have 1, root 3, and 2. Cosine of 30 is root 3 over 2. Now, if you look at the left-hand side of the equation, we have negative pi over 6. That's a quadrant 4 angle. But we know, using our concept of all students take calculus, that cosine in quadrant 4 is positive. Therefore, the left-hand side of this gives you positive root 3 over 2. If we then look at the cosine of pi over 6, that's a quadrant 1 angle, and cosine is also positive in quadrant 1. So this gives you root 3 over 2. Therefore, if you ever put a negative angle into cosine, it will give you the same answer as the positive angle. This also works for his reciprocal function, which is secant. So if we had the secant of negative x, that is equal to the secant of x. Cosine and secant are even, and the other 4 trig functions are odd.